Space is often described as beautiful. We see glowing nebulae, endless star fields, and spiral galaxies stretching across the darkness. From a distance, the universe looks peaceful, calm, almost gentle. But the universe is not gentle. Beyond the light of our sun, beyond the planets we know, beyond even the nearest stars, there are regions so extreme and so unforgiving that survival becomes impossible. Places where gravity crushes matter into oblivion. Places where radiation burns hotter than millions of suns. Places where even time itself begins to behave differently. If you're ready to explore the most terrifying locations in the universe, make sure to subscribe to our channel. Hit the like button to support our cosmic journey, and share this video with anyone fascinated by the mysteries of space. Tonight, we begin a journey into the most terrifying locations in the universe. Not terrifying in the way of horror stories or shadows in the dark, but terrifying in scale, in power, in indifference. Because the most frightening thing about the universe is not that it is violent. It is that it does not care. On Earth, danger usually gives warning. Storms gather clouds. Volcanoes rumble. Predators make noise. But in space, there is no sound. No atmosphere to carry a scream. No air to vibrate with a warning. There is only silence. Complete, endless silence. Human beings evolved under a blue sky with a solid ground beneath their feet. Our minds are built for sunlight, gravity, and horizons. Space offers none of these comforts. There is no up or down. No surface to stand on. No air to breathe. Only an abyss in every direction. And somewhere inside that abyss are places so extreme that if you drifted too close, there would be no escape. No second chance. No rescue. So what makes a place truly terrifying in the universe? It is not simply darkness. Space is dark almost everywhere. It is not simply isolation. The entire cosmos is vast and mostly empty. What makes a place terrifying is when the laws of nature themselves begin to stretch to their limits. When gravity becomes overwhelming. When temperatures rise beyond imagination. When magnetic fields become strong enough to tear atoms apart. And in some places, time slows down. Black holes are the ultimate example. They are not holes in the way we imagine. They are not tunnels or cosmic whirlpools sucking everything in like a vacuum cleaner. A black hole is what remains when a massive star dies and collapses under its own gravity. The collapse is so complete, so total, that all of its mass compresses into an unimaginably small point. The result is an object with gravity so strong that nothing can escape it. Not dust. Not gas. Not even light. If light cannot escape, then what hope would anything else have? Surrounding every black hole is a boundary known as the event horizon. This is the point of no return. Cross it, and escape becomes impossible. No engine, no technology, no force in the known universe can bring you back. What makes this even more unsettling is that you would not see a black hole the way you see a planet or a star. It does not glow on its own. It does not shine. It hides against the darkness of space. You would only know it is there when the stars behind it begin to distort. When light bends in strange arcs around an invisible center. When space itself curves like fabric being pulled tight. Black holes do not chase. They do not hunt. They simply exist. Silent. Patient. Waiting. And somewhere, at the very center of our own galaxy, there is one. Our solar system orbits within the Milky Way, a galaxy containing hundreds of billions of stars. For centuries, we looked toward its bright band across the night sky without knowing what lay at its core. Now we know. At the heart of the Milky Way lies a supermassive black hole called Sagittarius A star. It is not a small remnant of a dead star. It is a gravitational giant containing the mass of millions of suns. Every star in our galaxy, including our own sun, moves under its influence. It sits there, 26,000 light-years away, hidden behind clouds of dust and gas, anchoring the entire galaxy together. And if we could travel there, if we could approach it slowly and carefully, we would witness one of the most terrifying sights in existence. In the next part of this journey, we will move closer to the center of the Milky Way. We will explore what would happen if you approached Sagittarius A star. How gravity would begin to distort space around you. How time itself would slow. And what it truly means to cross the edge of no return. If you are fascinated by the extreme, the mysterious, and the unimaginable depths of the cosmos, make sure you stay with us for this entire journey. There is so much more to uncover, and the deeper we go, the more unsettling the universe becomes. This is only the beginning. At the very center of our galaxy lies something extraordinary. Hidden behind thick clouds of cosmic dust and swirling gas, 26,000 light-years from Earth, there exists a gravitational giant that holds the Milky Way together. It does not shine like a star. It does not glow with visible light. Yet its presence controls the motion of hundreds of billions of stars. This object is called Sagittarius A star. Sagittarius A** is a supermassive black hole containing the mass of about 4 million suns compressed into a region no larger than our solar system. Every star in the Milky Way, including our own sun, orbits the galactic center because of its immense gravitational pull. It is the quiet anchor of our galaxy. And it is one of the most terrifying places we could ever imagine visiting. From Earth, Sagittarius A** appears harmless. It is far away, silent, and invisible to the naked eye. But if you could travel toward it, leaving behind the familiar spiral arms of the Milky Way, the environment would begin to change. Stars would grow more densely packed. Their orbits would become faster and more chaotic. Radiation levels would increase. The region near the galactic center is far more violent than the calm neighborhood around our sun. As you move closer, you would not see a giant swirling hole in space. Instead, you would notice something stranger. The stars behind the black hole would begin to distort. Light itself would bend, curving around an invisible center. This bending of light is caused by gravity. According to Einstein's theory of general relativity, massive objects warp the fabric of space and time. A black hole warps it so severely that space curves inward like a funnel with no bottom. The closer you drift toward Sagittarius A**, the stronger this curvature becomes. At a safe distance, you could orbit it just like any other massive object. In fact, many stars already do. Astronomers have observed stars whipping around Sagittarius A** at incredible speeds, completing orbits in just a few years. These observations confirmed its existence and revealed its enormous mass. But survival depends entirely on distance. If you continued approaching, gravity would begin to feel different. Not just stronger, but uneven. The side of your spacecraft closer to the black hole would feel a stronger pull than the side farther away. This difference in gravitational force is called a tidal force. At first, it would be subtle. Then it would become extreme. If you ventured too close, those tidal forces would stretch your spacecraft. The front would be pulled harder than the back. The structure would strain. Metal would begin to deform. And if you were unprotected, the same force would act on your body. This process has a strange name, Spaghettification. Spaghettification happens because gravity near a black hole increases dramatically over very short distances. Your feet, being slightly closer to the black hole than your head, would experience a stronger pull. The difference would stretch you vertically while compressing you horizontally. You would not be crushed immediately. You would be stretched. Longer and thinner. Like a strand of spaghetti. The closer you move to the event horizon, the more extreme this stretching would become. Eventually, the forces would exceed the strength of atoms themselves. Molecules would separate. Atoms would be torn apart. Matter would be pulled into a thin stream spiraling toward the center. But something even stranger would be happening at the same time. Time would begin to slow down. To an outside observer watching from a safe distance, your spacecraft would appear to move more and more slowly as it approached the event horizon. Your clocks would tick slower. Your movements would stretch out. Right at the edge, you would appear frozen in time. Light leaving your spacecraft would become increasingly redshifted, stretched into longer wavelengths as it fought against gravity. Eventually, you would fade from view, becoming dimmer and dimmer until you disappeared entirely. From your own perspective, however, time would feel normal. You would not notice your clock slowing. You would not sense time behaving differently. Instead, the rest of the universe would appear to speed up. The outside cosmos would seem to accelerate into the future. Stars would move faster in the sky. Galactic light would shift. If you could survive long enough near the event horizon, you might witness thousands, even millions of years of cosmic evolution unfolding in what feels like moments. This is gravitational time dilation. The stronger the gravity, the slower time passes relative to regions farther away. At the event horizon itself, escape velocity equals the speed of light. Once crossed, all possible paths forward lead inward. There is no direction you can travel that does not take you closer to the center. And that is what makes Sagittarius A** so terrifying. It is not simply that it destroys matter. It rewrites the rules of reality. Inside the event horizon, our current understanding of physics breaks down. At the very center lies what is called a singularity, a point where density becomes infinite and spacetime curvature becomes extreme beyond calculation. We do not yet know what truly happens there. Our equations stop working. Our models collapse. It is a boundary not just in space, but in knowledge. And yet, Sagittarius A** is not aggressively consuming everything around it. Right now, it is relatively quiet. It feeds slowly on stray gas and the occasional star that wanders too close. Compared to the luminous, violently feeding black holes in distant galaxies, it is almost calm. But calm does not mean safe. If Sagittarius A** were suddenly replaced with a visible object of equal mass, the orbits of the stars in the Milky Way would not change dramatically. Gravity at large distances depends only on mass, not on whether that mass is a star or a black hole. That is another unsettling truth. Black holes are not cosmic vacuum cleaners pulling everything in from across the galaxy. You must get dangerously close before they become lethal. But if you do get close, there is no negotiation. No survival strategy. No escape. Sagittarius A** reminds us that at the heart of our galaxy lies an abyss. A region where light cannot return, where matter is stretched beyond recognition, and where time itself slows to a near halt. And this is only one black hole. There are others far larger. Far more powerful. Some so massive that they make Sagittarius A** seem almost modest by comparison. Next, we will travel beyond our galaxy to explore one of the largest known black holes in the universe, an object so enormous that it challenges our understanding of how such giants can even exist. The deeper we go, the more terrifying the universe becomes. If Sagittarius A** is a giant, then what we are about to explore is something far beyond that. Far outside our galaxy, billions of light-years away, there exists one of the most massive black holes ever discovered. Its name is TON 618. TON 618 is not just large. It is almost incomprehensible. It contains an estimated mass of around 60 billion suns. Not millions. Billions. If our Sun were replaced by TON 618's mass, the gravitational dominance would extend far beyond anything we experience in our solar system. To understand how extreme this is, we need perspective. Sagittarius A**, the black hole at the center of our galaxy, contains about 4 million times the mass of the Sun. That already sounds enormous. But TON 618 outweighs it by more than 10,000 times. It is what astronomers call an ultramassive black hole. TON 618 sits at the center of a quasar, one of the brightest objects in the universe. A quasar forms when a supermassive black hole is actively feeding on enormous amounts of gas and dust. As matter spirals inward, it forms an accretion disk that heats up to extraordinary temperatures, emitting vast amounts of radiation. In fact, the light from TON 618's quasar outshines entire galaxies. What makes this even more terrifying is that the black hole itself remains invisible. The brightness we see comes from the material being destroyed as it falls inward. Now imagine its physical size. The event horizon of TON 618 stretches across a diameter estimated to be more than 240 billion kilometers. To compare, the distance from the Sun to Pluto is about 6 billion kilometers at most. That means TON 618's event horizon would extend far beyond Pluto's orbit. If placed at the center of our solar system, its surface of no return would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. The entire known planetary system would fit comfortably inside it. And that is just the event horizon. Beyond that boundary lies the accretion disk, a blazing ring of superheated gas that could extend even farther. Temperatures within that disk reach millions of degrees. Radiation levels would be instantly lethal. The environment around TON 618 is not just gravitationally extreme. It is violently energetic. Now consider the scenario: what if TON 618 replaced our Sun? At first, something surprising would happen. If the Sun were magically swapped with a black hole of equal mass, Earth's orbit would remain the same. Gravity at a distance depends on mass, not on whether that mass is a star or a black hole. But TON 618 does not have equal mass to our Sun. It has 60 billion times more. If it suddenly appeared in place of the Sun, the gravitational balance of the solar system would be destroyed instantly. Every planet would experience a massive increase in gravitational pull. Orbital speeds would no longer be sufficient to maintain stable paths. Earth would begin accelerating inward. There would be no explosion. No dramatic blast outward. Instead, the planet would fall. As Earth spiraled toward TON 618, tidal forces would begin tearing it apart long before it reached the event horizon. Oceans would rise catastrophically. The crust would fracture. The entire planet would stretch under uneven gravitational pull. Eventually, Earth would break apart into streams of molten rock, pulled into a glowing spiral of destruction. But even that dramatic scenario does not fully capture the scale of TON 618. Its gravitational influence extends across enormous distances. The region around it is not a quiet galactic neighborhood. It is a feeding zone. Gas clouds stretch for light years, slowly drifting inward. Stars that wander too close are shredded, forming brilliant flares as their matter is consumed. The energy released when matter falls into TON 618 is staggering. A single star being torn apart could release more energy than our Sun will emit in its entire lifetime. And yet, from far away, it would still appear as just another point of light in the sky. That is one of the most unsettling aspects of black holes. Their true scale hides behind distance. If you attempted to approach TON 618 in a spacecraft, you would face a different kind of terror compared to Sagittarius A star. Because TON 618 is actively feeding, the environment would be far more violent. Radiation would intensify long before you neared the event horizon. High-energy particles would bombard your ship. The surrounding space would glow with lethal brightness. As you moved closer, the accretion disk would dominate your view. It would not look like a simple ring. It would appear warped and distorted due to gravitational lensing. Light from the far side of the disk would bend over the top, creating strange arcs and halos. Time dilation would again become noticeable. To distant observers, your descent would appear to slow dramatically as you approached the event horizon. Signals sent back would grow weaker and more redshifted. Eventually, they would fade entirely. From your own perspective, however, the fall would continue. Crossing the event horizon of such a massive black hole might actually be less immediately violent than falling into a smaller one. Because TON 618 is so large, the tidal forces at its event horizon would be less extreme compared to smaller black holes. You might cross the boundary without immediate spaghettification. But deeper inside, as you move closer to the singularity, those forces would grow catastrophic. There would be no survival. No return. No evidence left behind. TON 618 challenges our understanding of how black holes grow so large. How could something reach 60 billion solar masses? Did it grow steadily over billions of years, or did it form rapidly in the early universe? Astronomers are still investigating. What we do know is that objects like TON 618 are among the most powerful gravitational engines in existence. They shape galaxies. They influence cosmic structure. They are not rare anomalies. Many galaxies appear to host supermassive black holes at their centers. Some may host monsters even larger than TON 618. When we look up at the night sky, we see stars and galaxies. But hidden within many of those galaxies are dark cores, silent and immense, controlling the motion of everything around them. Sagittarius A* is terrifying because it anchors our home galaxy with an invisible abyss. TON 618 is terrifying because it reveals how extreme black holes can become. And yet, there is another kind of fear. Not the fear of a massive object fixed at the center of a galaxy. But the fear of something wandering. Unseen. Unpredictable. Black holes that drift alone through interstellar space, not anchored to any galaxy's core. In the next segment, we explore rogue black holes, invisible predators moving through the darkness with no warning at all. The universe does not need to be close to be dangerous. Sometimes, danger drifts silently toward you. So far, we have explored black holes that sit at the centers of galaxies. Massive anchors, holding billions of stars in orbit. But not all black holes stay in one place. Some wander. Alone. Across the vast emptiness between stars. These are known as rogue black holes. A rogue black hole forms in several ways. Sometimes, when two galaxies collide, their central black holes eventually merge. During that violent interaction, gravitational forces can slingshot one of them away at incredible speeds. In other cases, when two black holes merge, the release of gravitational waves can create a recoil effect powerful enough to eject the newly formed black hole from its host galaxy. The result is an object with immense mass, no longer bound to a galactic center, drifting through interstellar or even intergalactic space. Unlike stars, rogue black holes emit no light of their own. Unlike quasars, they may not be actively feeding. They are almost completely invisible. And that is what makes them deeply unsettling. If a star is a lighthouse in the dark, a rogue black hole is the opposite. It moves without illumination, without sound, without warning. Imagine a region of space where stars are spread far apart, separated by trillions of kilometers. In that darkness, a black hole could be traveling for millions or even billions of years, undetected. You would not see it coming. You would not hear it. You would only notice its presence when gravity began to distort the motion of nearby objects. Astronomers believe there could be millions, possibly even billions, of stellar mass black holes drifting throughout the Milky Way alone. Most would be the remnants of massive stars that exploded in supernovae long ago. If those explosions were asymmetrical, they could have given the newborn black holes a kick, sending them traveling through space. Some of these rogue black holes might be only a few times the mass of the Sun. Others could be far larger. The terrifying question is not whether they exist. It is how close one could come without us knowing. Space is unimaginably vast. The nearest star beyond our Sun is over 4 light-years away. On human scales, the chance of a rogue black hole wandering directly into our solar system is extremely small. But extremely small is not the same as impossible. If a rogue black hole passed through the outer regions of our solar system, the first signs would be subtle. The orbits of distant objects, such as comets in the Oort cloud, might begin to shift. Long, stable paths would become distorted. Comets could be flung inward toward the Sun. Gravitational balance would slowly unravel. If the black hole came closer, the effects would grow stronger. Planetary orbits could stretch into elongated ellipses. Some planets might be pulled inward. Others could be flung outward into deep space. And still, you would see nothing. No glowing sphere approaching in the sky. No visible shape. Only the quiet rearrangement of gravity. If Earth were to pass dangerously close to a rogue black hole, tidal forces would begin to act on the planet. Oceans would surge. The crust would strain. Earthquakes would intensify as gravitational gradients pulled unevenly across the planet's diameter. If the encounter were close enough, Earth could be torn apart entirely, stretched into a stream of debris spiraling inward. But even a near miss would be catastrophic. A slight change in Earth's orbit could alter temperatures drastically. Too close to the Sun, and oceans could evaporate. Too far, and the planet could freeze. All caused by something we cannot see. There is another disturbing possibility. A rogue black hole might carry with it remnants of a system it once belonged to. It could have captured asteroids, gas clouds, or even planets in orbit around it. Imagine a dark object drifting through space with frozen worlds circling an invisible center. Planets without sunlight. Worlds lit only by distant stars. The idea challenges our sense of stability. We are used to thinking of planetary systems as orderly, centered around stars. But rogue black holes represent chaos. They are gravitational nomads. Astronomers have begun detecting candidates for rogue black holes through gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the star's light, temporarily magnifying it. By carefully analyzing these distortions, scientists can infer the presence of otherwise invisible objects. In recent years, evidence has suggested that some of these lensing events may indeed be caused by isolated black holes drifting through space. They are out there. Silent. Unlit. Unstoppable. Yet it is important to remember that space is vast beyond comprehension. Even if millions of rogue black holes wander the Milky Way, the distances between stars are so enormous that direct encounters remain rare. Still, the possibility lingers. Right now, somewhere in the galaxy, a black hole could be traveling through the dark. It may have been wandering for billions of years. It may continue wandering long after our sun has burned out. And we would never know unless it came close enough to bend the light of distant stars or disturb the orbits of objects in its path. Rogue black holes represent a different kind of terror than the supermassive giants at galactic centers. Sagittarius A** stays where it is. Ton 618 dominates its host galaxy. But rogue black holes move. They drift through the cosmic ocean like unseen currents, carrying immense gravitational power with them. They do not need to roar. They do not need to shine. They only need to pass nearby. As we continue deeper into the most terrifying locations in the universe, we will move beyond black holes and explore planets that defy imagination. Worlds of fire, glass, and eternal darkness. Because the universe does not reserve its horrors for empty space alone. Sometimes, entire planets become places where survival is impossible. And some of them are more extreme than anything we have imagined. Not all terrifying places in the universe are empty voids or collapsing stars. Some are planets. Entire worlds that orbit their stars just as Earth orbits the Sun. From a distance, they may appear ordinary. Spheres of rock or gas circling a source of light. But up close, these worlds are anything but ordinary. They challenge what we think a planet should be. They exist in environments so extreme that the very idea of standing on them becomes impossible. These are planets that should not exist. The first is called WASP-12b. WASP-12b is what astronomers call a hot Jupiter, a gas giant similar in size to Jupiter but orbiting incredibly close to its parent star. While Earth takes 365 days to orbit the Sun, WASP-12b completes a full orbit in just over one Earth day. It is so close to its star that its atmosphere is being pulled away. The gravity of the star stretches the planet into an egg-like shape. Instead of being a perfect sphere, WASP-12b is elongated, distorted by tidal forces that constantly strain its structure. Imagine Jupiter drifting closer and closer to our Sun until its outer layers begin to peel away like steam rising from boiling water. That is what is happening to WASP-12b. The star's gravity is literally eating it. Streams of gas are being siphoned from the planet, forming a glowing trail as the material spirals toward the star. Over time, this process will continue until the planet is completely consumed. If Earth were placed at the same distance from our Sun, our oceans would vaporize almost instantly. The atmosphere would be stripped away. The surface would melt into magma. Within a short time, nothing recognizable would remain. WASP-12b shows us a future where a planet does not simply orbit its star. It is devoured by it. Next is HD 189733b. At first glance, HD 189733b appears almost beautiful. Observations suggest it has a deep blue color, not unlike Earth seen from space. But this similarity is deceiving. The blue hue does not come from oceans. It comes from silicate particles in the atmosphere, tiny fragments of glass. On this planet, temperatures soar above 800 degrees Celsius. The atmosphere is thick with vaporized rock. Winds rage across the planet at speeds exceeding 8,000 kilometers per hour, far faster than the speed of sound on Earth. Under these conditions, glass forms in the atmosphere and is blown sideways by supersonic winds. It does not fall gently like rain. It slices through the air horizontally. Imagine standing in a storm where shards of molten glass travel faster than bullets. There would be no shelter. No protection. The atmosphere itself would become a weapon. On Earth, our strongest hurricanes can reach wind speeds of a few hundred kilometers per hour. They are devastating. Yet compared to HD 189733b, even the most violent storms on Earth seem mild. This is a world where the sky itself cuts. Now consider 55 Cancri. This planet is often called a super-Earth because it is larger and more massive than our planet, yet still rocky in composition. But its environment is nothing like Earth's. 55 Cancri East orbits so close to its star that a year there lasts just 18 Earth hours. One side of the planet permanently faces the star, locked in place by tidal forces. The same hemisphere experiences constant daylight, while the opposite side remains in eternal darkness. On the day side, temperatures climb above 2000 degrees Celsius. At these extremes, rock melts. Scientists believe vast oceans of lava may cover the surface, glowing red beneath a sky thick with heat and pressure. Entire continents could be molten, churning slowly under relentless stellar radiation. The night side, however, may be significantly cooler. Not comfortable, but cooler than the blazing hemisphere facing the star. On Earth, our rotation ensures that no region remains under constant sunlight or permanent darkness. Day and night cycle predictably. Temperatures fluctuate within ranges that allow liquid water and life. On 55 Cancri, balance does not exist. It is a world divided between fire and shadow. And then there is Trace 2b. Trace 2b is one of the darkest planets ever discovered. It reflects less than 1% of the light that hits it. Coal reflects more light. Even black acrylic paint would appear brighter. Scientists are not entirely sure why it is so dark. Its atmosphere may contain chemicals that absorb nearly all incoming light, trapping it instead of scattering it back into space. If you could approach Trace 2b, you would see almost nothing. Even though it orbits close to its star, its surface would appear as a shadow against the glow. It would be darker than night. On Earth, darkness still allows reflection. Moonlight, starlight, city lights, even in remote places, something reflects back. But Trace 2b absorbs almost everything. It is a planet that hides in plain sight. These worlds force us to reconsider what a planet can be. On Earth, we measure comfort by the presence of water, breathable air, and moderate temperatures. We think of planets as potential homes, as places that might someday resemble ours. But the universe does not prioritize comfort. Some planets are stretched apart by their stars. Some are carved by supersonic glass storms. Some glow with oceans of lava under permanent daylight. Some swallow nearly all light, becoming darker than anything we have known. And these are only a handful among thousands of exoplanets already discovered. As detection methods improve, we continue to find worlds that challenge our imagination. Planets with iron rain. Planets with temperatures colder than deep space. Planets orbiting dead stars. Each discovery expands our understanding, but it also deepens the sense of how rare and fragile Earth may be. Our planet sits at just the right distance from the Sun. Our atmosphere shields us. Our magnetic field protects us from solar radiation. Liquid water flows across our surface. Compared to WASP-12b, we are not being consumed. Compared to HD 189733b, our skies do not rain glass. Compared to 55 Cancri E, we are not locked in eternal fire. Compared to Trace 2b, we shine. The universe is filled with worlds that should not exist, yet they do. Worlds shaped by extreme gravity, intense radiation, and violent proximity to their stars. And if planets can become this hostile, imagine what happens when stars themselves die. In the next hour, we move from impossible planets to the remnants of exploded stars, neutron stars, magnetars, and cosmic explosions powerful enough to outshine entire galaxies. The deeper we travel, the more intense the universe becomes. Stars may appear eternal when we look at the night sky. They shine steadily, night after night, year after year. But stars are not permanent. They are massive nuclear engines, constantly balancing the inward pull of gravity with the outward pressure of fusion. When that balance fails, the result can be catastrophic. Some of the most terrifying locations in the universe are not planets or black holes, but the remains of dead stars and the explosions that create them. We begin with neutron stars. When a massive star reaches the end of its life, it runs out of nuclear fuel. Fusion slows, pressure drops, and gravity takes over. The core collapses in a fraction of a second. Outer layers rebound in a violent explosion known as a supernova. For a brief time, that single star can outshine an entire galaxy. What remains after the explosion depends on the original mass of the star. If it is not massive enough to form a black hole, the core compresses into something almost equally extreme. A neutron star. A neutron star is what happens when gravity crushes matter beyond normal atomic structure. Protons and electrons are forced together, forming neutrons. The result is an object with the mass of the Sun compressed into a sphere only about 20 kilometers across. To put that into perspective, imagine compressing something as massive as our Sun into a city-sized sphere. The density is almost impossible to comprehend. A single teaspoon of neutron star material would weigh billions of tons on Earth. Not millions. Billions. If you could somehow place that teaspoon on our planet, it would punch straight through the crust, sinking toward the core under its own weight. The surface gravity of a neutron star is immense. If you stood on one, which would already be impossible due to radiation and pressure, your body would be crushed instantly. Yet neutron stars are not simply dense. They spin. Because of conservation of angular momentum, when the original star collapses, it begins rotating faster and faster. Some neutron stars spin several hundred times per second. Their rotation is so precise that they can act like cosmic clocks. These are known as pulsars, emitting beams of radiation that sweep across space like lighthouse beams. But some neutron stars go even further. They become magnetars. One of the most extreme examples ever observed is SGR 1806-20. SGR 1806-20 is a magnetar located in our galaxy. Magnetars are neutron stars with magnetic fields so powerful that they defy normal comparison. The magnetic field of Earth protects us from solar radiation. It guides compasses and shapes auroras near the poles. It is strong enough to influence charged particles in space. A magnetar's magnetic field is trillions of times stronger. If SGR 1806-20 were placed halfway between Earth and the Moon, its magnetic field would disrupt electronics across our planet. Credit cards would be wiped. Hard drives would fail. Data storage systems would be erased. Not by heat. Not by impact. By magnetism alone. In 2004, SGR 1806-20 released a giant flare, a sudden burst of energy that briefly became one of the brightest events ever detected in our galaxy. Even from about 50,000 light-years away, it affected Earth's upper atmosphere. That is the scale of energy involved. Now imagine standing closer. The magnetic forces near a magnetar are so intense they can distort atoms. They can stretch electron clouds into elongated shapes. Matter behaves differently under such extreme fields. The crust of a magnetar can fracture under magnetic stress, releasing bursts of gamma rays and X-rays into space. These starquakes are unlike anything we experience on Earth. Neutron stars and magnetars are terrifying not only because of their density or magnetism, but because they represent matter pushed to its absolute limits. But even they are not the most powerful explosions in the universe. For that, we must look at gamma-ray bursts. Gamma-ray bursts are the most energetic explosions known since the Big Bang. They occur when massive stars collapse into black holes or when neutron stars merge in violent collisions. For a few seconds, a gamma-ray burst can release more energy than our Sun will emit over its entire 10 billion-year lifetime. These bursts send narrow jets of gamma radiation traveling across the universe at nearly the speed of light. If one of those jets were aimed directly at Earth from relatively close range, the consequences could be devastating. Gamma rays carry enormous energy. They can strip electrons from atoms, break molecular bonds, and damage biological tissue at the cellular level. A nearby gamma-ray burst could deplete the ozone layer, exposing Earth's surface to harmful ultraviolet radiation from the Sun. It could disrupt ecosystems, trigger climate changes, and cause mass extinctions. Fortunately, most gamma-ray bursts occur in distant galaxies, far beyond any threat to us. And even within our own galaxy, the chances of one being aimed directly at Earth are extremely low. But low probability does not mean zero. The universe has produced these events many times before. Evidence suggests that past gamma-ray bursts may have influenced extinction events on Earth. They are rare. But when they occur, they are unstoppable. After the explosion fades, what remains is often a supernova remnant. Supernova remnants are vast, expanding clouds of gas and dust, glowing with the energy of the original explosion. They can span dozens of light-years. Filaments of ionized gas twist and curl through space, forming structures of haunting beauty. These remnants seed the cosmos with heavy elements. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged inside stars and scattered into space by supernova explosions. In that sense, we are made from the debris of dying stars. There is beauty in that idea. But there is also violence. The same explosion that creates the elements necessary for life is powerful enough to sterilize nearby planetary systems. Any world orbiting too close to a supernova would be bathed in intense radiation, its atmosphere stripped away. Supernova remnants are both creative and destructive. They are the aftermath of death, expanding slowly into space, marking where a star once shone. As we look deeper into the universe, we see countless examples of stellar death. Some leave behind neutron stars. Some create magnetars. Some collapse into black holes. Some produce gamma-ray bursts that flash across billions of light-years. Each represents a location where physics reaches extremes. Each is a reminder that stars are not eternal. And if stars can die so violently, what happens in the chaotic regions where new ones are born? In the next hour, we travel into stellar nurseries, vast nebulae filled with radiation, shockwaves, and newborn stars carving through clouds of gas. Because even creation, in the universe, can be terrifying. When we see images of nebulae captured by space telescopes, they appear peaceful. Vast clouds of color suspended in darkness. Soft blues, glowing pinks, deep purples stretching across light years of space. They look calm. But many of these regions are anything but calm. They are battlegrounds of gravity, radiation, shock waves, and stellar birth. Places where matter collapses, ignites, and explodes. Places where new stars are born in violence. One of the most famous of these regions is the Orion Nebula. Located about 1,300 light-years from Earth, the Orion Nebula is one of the closest massive star-forming regions to our planet. To the naked eye, it appears as a faint blur in the constellation Orion. Through telescopes, it reveals a glowing cloud of gas and dust stretching over 20 light-years. Inside this nebula, gravity is pulling hydrogen gas together into dense clumps. As these clumps collapse, temperatures rise. Pressure builds. Eventually, nuclear fusion ignites, and a new star is born. But star birth is not gentle. Young stars emit intense ultraviolet radiation. They produce powerful stellar winds that blast surrounding gas outward at high speeds. Shock waves ripple through the nebula, compressing some regions while tearing others apart. If Earth were somehow placed within the Orion Nebula near one of these young massive stars, the radiation would strip away our atmosphere. High-energy ultraviolet light would break apart molecules. Solar winds far stronger than those from our Sun would erode the planet's surface over time. The Orion Nebula is a stellar nursery. But nurseries in space are chaotic. Stars compete for material. Gravity pulls gas inward while radiation pushes it away. Massive stars live fast and die young, often exploding as supernovae within the same region where they formed, sending shockwaves back through the cloud. Creation and destruction happen side by side. Another iconic structure within a star-forming region is known as the Pillars of Creation. The Pillars of Creation are located within the Eagle Nebula, thousands of light-years away. They appear as towering columns of gas and dust, stretching for several light-years into space. Their shape is both elegant and haunting, like cosmic cliffs carved from interstellar clouds. But those pillars are not solid structures. They are being sculpted by radiation. Massive young stars nearby emit intense ultraviolet light, which erodes the surrounding gas. The radiation ionizes the outer layers, heating and dispersing them into space. What remains are denser regions that resist erosion slightly longer, forming the pillar-like shapes we see. Over time, even these pillars will disappear. In fact, astronomers believe a supernova explosion may have already partially destroyed them. Because light takes time to travel, we may be seeing an image of the pillars as they existed thousands of years ago. In reality, parts of them may no longer exist. They are temporary monuments to stellar violence. Inside these columns, new stars are forming. Gravity continues pulling gas inward even as radiation pushes outward. It is a constant struggle between collapse and dispersal. If our solar system were placed inside such a region, the intensity of radiation would make stable planetary atmospheres difficult to maintain. The frequent shockwaves from nearby stellar activity could disrupt orbits. The environment would be unpredictable and unstable. And yet, this is how many stars, possibly including our own Sun, were born. Violence is part of cosmic creation. But the scale of violence increases even further when entire galaxies collide. Right now, our galaxy, the Milky Way, is moving toward a future encounter with the Andromeda Galaxy. The Andromeda Galaxy is the nearest major galaxy to us, located about 2.5 million light-years away. It is slightly larger than the Milky Way and contains hundreds of billions of stars. And it is moving toward us. At approximately 4 billion years from now, the Milky Way and Andromeda will begin to merge. At first, this may not sound terrifying. Space within galaxies is so vast that direct star-to-star collisions are unlikely. But that does not mean the event will be peaceful. As the galaxies approach each other, their gravitational fields will begin to distort their shapes. Spiral arms will stretch and twist. Streams of stars will be flung outward into intergalactic space. Vast clouds of gas will collide, compressing violently and triggering waves of star formation. The night sky, if viewed from Earth at that time, would be unrecognizable. Andromeda would grow larger and larger, eventually spanning a huge portion of the sky. Stars would appear in new positions. Tidal forces could alter the Sun's orbit within the galaxy. There is even a small possibility that our solar system could be thrown into a different region of the merged galaxy, perhaps farther from the galactic center, or possibly closer. While individual stars are unlikely to collide directly, gravitational disturbances could disrupt distant comet reservoirs like the Oort cloud, sending icy bodies inward toward the inner solar system. Over hundreds of millions of years, the two galaxies will pass through each other multiple times, gradually merging into a single, larger elliptical galaxy. This is not a sudden crash like two cars colliding. It is a slow-motion cosmic transformation. Yet it is still violent on a galactic scale. Massive bursts of star formation will ignite. Supernovae will increase in frequency. Black holes at the centers of both galaxies will eventually spiral toward one another and merge, releasing powerful gravitational waves. The calm spiral shape of the Milky Way will be gone. In its place will be something new. Galactic collisions are a reminder that even structures spanning hundreds of thousands of light-years are not permanent. Gravity reshapes everything over time. The Orion Nebula shows us the chaos of star birth. The pillars of creation reveal how radiation sculpts and destroys even the most beautiful cosmic structures. The future collision with Andromeda reminds us that galaxies themselves are temporary forms in a constantly evolving universe. Violence is not rare in space. It is fundamental. In the next hour, we will move away from explosive regions and into a different kind of terror, the coldest and darkest places in existence. Regions where heat disappears, light fades, and isolation becomes absolute. Because sometimes, the most terrifying thing in the universe is not fire. It is the absence of it. Not all terrifying locations in the universe are filled with heat, explosions, or intense radiation. Some are defined by cold, darkness, and isolation. Places where life as we know it could never survive. Places where even the simplest physical processes are slowed to extremes. One of the coldest known places in the universe is the Boomerang Nebula. Located about 5,000 light-years away in the constellation Centaurus, the Boomerang Nebula is a cloud of gas expanding outward from a dying star. What makes it remarkable is its temperature. While the background of space is already cold, about 2.7 Kelvin, the Boomerang Nebula is even colder. Observations suggest its temperature drops to just 1 degree above absolute zero. At these temperatures, molecules move almost imperceptibly. Heat barely exists. Matter itself behaves differently than anything we experience on Earth. The Boomerang Nebula is a place frozen in time, a cosmic freezer stretching across light-years. If a planet or spacecraft were inside this cloud, it would be instantly frozen. The energy of atoms would slow to a crawl. Any chemical reactions necessary for life would cease. It is a place where existence itself is suspended. Even colder is the darkness of intergalactic space. Between galaxies lie regions called intergalactic voids. These are vast expanses where few stars, gas clouds, or planets exist. Essentially, They are the universe's empty spaces on the grandest scale. Some voids span hundreds of millions of light-years across. Inside a void, the distances between any matter are so vast that the concept of proximity loses meaning. A single galaxy could drift for millions of light-years without encountering another galaxy. Light is sparse. Radiation is minimal. Heat is almost non-existent. Imagine being stranded in such a void. There would be no sunlight. No planets. No stars to navigate by. No cosmic landmarks. Even if you were moving at the speed of light, reaching another galaxy could take billions of years. This is almost absolute emptiness. Eternal isolation. A place where the universe seems to vanish around you. A place where even time can feel meaningless because nothing happens for billions of years. Adding to this terror are rogue planets. Rogue planets are worlds that drift through space without a star. Unlike Earth, they have no sun to provide warmth, light, or energy. They may have formed in a solar system and been ejected by gravitational interactions, or they may have formed independently. Either way, they float alone in the cold. Without a star, a rogue planet freezes. Surface temperatures drop to hundreds of degrees below zero. Any atmosphere it has may condense or freeze entirely. Liquid water becomes impossible. Life as we know it could not survive. Some of these planets wander through the darkness indefinitely, perhaps for billions of years. They may encounter nothing at all, drifting silently through the interstellar void, invisible to any observer. Imagine standing on the surface of a rogue planet. The sky is black, even in what would normally be daytime. No light reaches you. No warmth. No stars visible except perhaps faint points far, far away. You are alone, and the cold is absolute. These cold and dark locations show us a different kind of cosmic terror. Not from explosions, gravity, or radiation, but from absence. From silence. From emptiness. From temperatures so low that matter itself behaves almost unnaturally. The Boomerang Nebula freezes matter to near absolute zero. Intergalactic voids stretch across unimaginable distances, almost devoid of energy or structure. Rogue planets drift in frozen isolation for eternity. In the universe, not all danger comes with fire or light. Sometimes, the most terrifying places are the ones where everything familiar disappears. In the next hour, we will explore the most extreme magnetic and gravitational environments in the universe, cosmic forces so powerful they can bend light, twist space, and tear matter apart. Because cold and dark are terrifying. But nothing rivals the raw, invisible forces that shape the cosmos. Not all terrifying worlds are planets. Some are moons, natural satellites orbiting planets, that harbor environments so extreme that survival would be impossible. The first is Io, one of Jupiter's largest moons. Io is a planet of fire and chaos. Its surface is constantly reshaped by volcanic eruptions, with hundreds of active volcanoes spewing lava across the landscape. Mountains are covered in molten rock. Sulfur compounds coat the surface in bright yellow, red, and orange hues. The heat is intense, the landscape ever-changing. Lava lakes form and solidify in days, only to be replaced by fresh flows. The sky is filled with volcanic plumes, sometimes hundreds of kilometers high. If you were standing on Io, the ground beneath you could erupt at any moment, reshaping the terrain and exposing deadly lava flows. Next, we visit Europa. Europa appears calm from a distance, a smooth, icy surface stretching across hundreds of kilometers. But beneath the ice lies a hidden ocean, a global layer of liquid water kept warm by tidal forces caused by Jupiter's immense gravity. This ocean may harbor conditions favorable to life, but the surface is deadly. Europa is bombarded by radiation from Jupiter's magnetic field at levels thousands of times higher than Earth. Even a short stay on the surface would be lethal without heavy shielding. Cracks in the ice hint at movement below. Ice plates shift and collide, creating massive ridges and canyons. The moon's surface is fractured, unstable, and constantly in motion. It is a world of hidden danger beneath a frozen facade. Moving further out, we find Titan. Titan is an alien world. Its atmosphere is thick with nitrogen and methane, dense enough that you could float if you jumped. The surface is dotted with lakes and rivers, but instead of water, these bodies are filled with liquid methane and ethane. Temperatures hover around -180 degrees Celsius. Methane rains fall in liquid form, forming seas, lakes, and rivers. The chemistry is alien. The air smells of hydrocarbons. Organic compounds float in the atmosphere, creating a toxic environment for humans. Titan's low gravity and thick atmosphere might seem inviting, but every aspect of this moon is hostile. Exposure to the atmosphere would quickly prove fatal. There is no warmth. No water to drink. No oxygen to breathe. Finally, we examine Enceladus. Enceladus is smaller than Titan, but it hides a deadly secret. Its surface is icy and bright, reflecting nearly all sunlight. Beneath the ice lies a subsurface ocean, and from cracks near the South Pole, powerful ice geysers blast water vapor and ice particles hundreds of kilometers into space. These geysers create an environment of constant hazards. Ice particles travel at high velocities, and any spacecraft or probe passing nearby must navigate carefully. Surface temperatures are frigid, averaging around -200 degrees Celsius. The combination of extreme cold, high-velocity ice, and subsurface oceans makes Enceladus a deadly place for any unprotected visitor. These moons reveal the diversity and extremity of environments in our solar system. Io is a world of molten fire. Europa hides oceans beneath lethal radiation. Titan is a frozen, methane-soaked alien landscape. Enceladus shoots deadly ice into space. They challenge our understanding of what a moon can be. They are not merely companions to planets, they are worlds of their own, shaped by tidal forces, radiation, and alien chemistry. If Earth is a safe haven, these moons are cosmic death zones. Visiting them would require shielding, technology, and knowledge far beyond our current capabilities. And yet, despite the danger, these moons are fascinating. They may hold clues to life elsewhere. They show the extremes of planetary physics. They are living laboratories of geology, chemistry, and cosmic forces. In the next hour, we leave moons behind to explore the most hostile exoplanets, worlds beyond our solar system, where conditions are so extreme that even gas giants and rocky planets are unrecognizable. The universe continues to push the boundaries of what is possible, and terrifying. Some of the most terrifying locations in the universe are not places we can see. They exist in theory. In physics and mathematics. In scenarios that challenge the limits of imagination and force us to consider the fragility of reality itself. We begin with dark matter regions. Dark matter makes up roughly 27% of the universe, yet we cannot see it. It does not emit light. It does not reflect light. We infer its presence only by its gravitational effects on visible matter. Regions dominated by dark matter are invisible structures that thread across galaxies and galaxy clusters. They form the scaffolding of the cosmos. Without them, galaxies could not hold together. Imagine drifting through one of these dark matter filaments. There is nothing to see. No stars, no planets, no light. Yet gravity subtly warps the paths of objects around you. Invisible forces pull and tug without warning. You would feel no heat, no radiation, no light. But space itself would behave differently. You would move along gravitational currents defined by something you cannot touch, cannot see, cannot understand fully. Next is a concept even more unsettling: false vacuum collapse. According to some theories in physics, the universe we inhabit might exist in a false vacuum, a temporary state of lower energy. If a more stable state exists, the universe could transition to it instantly. A bubble of true vacuum could form anywhere, expanding at the speed of light. It would rewrite the laws of physics inside it. Atoms, molecules, even fundamental forces could cease to exist as we know them. There would be no warning. No way to escape. The universe as we understand it would end in an instant. No explosions. No light. No time. Only absolute transformation. Another theoretical nightmare is the Big Rip. The universe is expanding, and observations suggest this expansion is accelerating. If that acceleration continues indefinitely, it could reach a point where it tears everything apart. Galaxies would separate. Stellar systems would disintegrate. Eventually, even atoms themselves could be torn apart as space stretches faster than the forces holding matter together. Imagine existing in a universe where not only planets and stars vanish, but matter itself is unmade. It is a future defined by relentless expansion. A slow, inevitable unraveling of the fabric of reality. Finally, we consider the possibilities raised by parallel universes and cosmic inflation. Cosmic inflation suggests the universe underwent rapid expansion in its earliest moments. Some theories propose this process continues elsewhere, producing an infinite number of universes. Each universe could have different physical laws, different dimensions, different realities entirely. For every version of our universe, there may exist countless variations, some almost identical, some completely alien. The sheer scale is staggering. Every choice, every variation of physics, every potential outcome may exist somewhere. The terror is subtle. It is not immediate danger. It is the understanding that infinity contains infinite possibilities, some comforting, some unimaginable. Slowly contemplating these theoretical nightmares forces a different kind of fear. Not fear of fire, cold, radiation, or gravity. But fear of limits, fragility, and the possibility that everything we know could be entirely contingent, small and insignificant in a vast and unpredictable multiverse. Dark matter, false vacuum collapse, the Big Rip, infinite parallel universes. They remind us that the universe is far stranger and more terrifying than any planet, star, or black hole we have observed. And as we take the final step in our journey, we move from theoretical nightmares back to observable reality. To the ultimate extreme, regions in the universe that combine heat, gravity, and radiation beyond comprehension, places that embody absolute terror in ways both seen and measurable. In the next hour, we confront the most extreme, most deadly locations the universe has to offer. Places no human could survive. Places that push physics itself to the limit. The universe is not eternal in its current state. Even the sun, our steady companion, will one day reach the end of its life. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core. Without fusion to counteract gravity, the core will contract while the outer layers expand. The sun will become a red giant. Its radius will stretch outward, engulfing Mercury, Venus, and possibly Earth. The heat will scorch our planet, boiling oceans, melting rock, and stripping away the atmosphere. Life as we know it will end. Eventually, the sun will shed its outer layers, leaving behind a dense, cooling remnant called a white dwarf. A glowing ember of a star, slowly fading over billions of years. But this is only the beginning. Far in the future, the universe itself faces its ultimate fate. Scientists call it the heat death of the universe. As stars burn their fuel, galaxies drift apart, and matter spreads ever thinner, the cosmos approaches maximum entropy. Energy becomes uniformly distributed. Stars burn out. Black holes evaporate. Galaxies vanish. Light fades. The universe becomes dark. Cold. Silent. Atoms themselves continue to exist, but the structure, the movement, the dance of energy, all ceases. Billions, then trillions, then quadrillions of years pass. The cosmos stretches into empty stillness. Eventually, even the white dwarfs left behind cool into black dwarfs, cold, dark stellar remnants. No heat. No light. No activity. Just frozen spheres drifting silently through space. At this stage, the universe has grown incomprehensibly old. Stars, planets, and galaxies are long gone. Only sparse particles of matter remain, scattered across the void. Thank you for watching this journey through the most terrifying locations in the universe. If you enjoyed this adventure, don't forget to subscribe for more cosmic explorations, like this video to support the channel, and share it with anyone who loves the mysteries of space. Your support helps us continue uncovering the universe's most extreme and breathtaking wonders.